Yes?
Yeah, it was.
Hi, I'm Simon from Canada, and this is my talk about the Ecdysis project that we've been doing for the last few months. Okay, so have you seen these graphs? You surely have. These are the graphs that say that the sky is falling. Just before I start, show of hands. Who here has played with IPv6? Raise your hand. Who usually has IPv6 connectivity? Okay. Different set of hands. Not a subset, it's strange. Who has set up a router, maybe OSPF3 routing, stuff like that? Okay, thank you. Okay, so this is the state of the IPv4 pool in IANA. So most of the addresses have been allocated. The IANA pool is what's left, and IETF reserved is what's reserved for, like RFC 1918 and other stuff. Okay. Just a second while I get used to my laptop. Okay, so as you know, not everything that is allocated is actually used. On this graph, you can see that what is advertised, and you can see that it is a pretty significant portion of what is reserved. And it's really hard to be more precise than that. You would actually need to poll, and not everything would respond, so on. This is the allocations of /8s given by IANA over time. We see that it's been steadily going up, and there is no sign of it slowing down. And this is a graph of the allocations actually made out by RIRs. It's smoother than the previous graph because RIRs give out smaller blocks than IANA does. But what's really interesting is the growth. And the growth is the usage of IP addresses. We can't know that, but we have something pretty close, which is the growth of advertised IP addresses. And this, to me, looks like an exponential growth function. So I show all these graphs to you to convince you that yes, the sky is falling, and now would be a good time to panic. And there is a lot of good data on IPv4.ru.net where I took these graphs, and they're automatically updated with the data that we have. So this is today's graph, and they all have regressions and different dates for when we're going to actually run out. So you've already seen this graph anyway. You probably haven't felt any pressure up to now. But you know that an exponential growth function, given an finite resource, it's only a matter of time. For example, we've been feeling some pressure lately when 1/8 was allocated to AppNIC by IANA very recently. So would you like to have an IP address in this range?
Sure.
Why? Why do you say sure?
Because
you can take the traffic. The problem with this address is that you're going to get, as soon as you advertise this, you're going to get DOS. Because a lot of stuff out there is badly configured, and you just receive a lot of traffic if you light this up. And it's an ongoing investigation, because AppNIC is not very happy with this. and they haven't started to allocate it yet to their customers, but their customers won't really be happy with this. So people are investigating, is it really that bad? Initial data points to yes. And there may be others that are bad also. My colleague has done some research, my colleague Marc Blanchet has done some research, and there are only 2/8s out there that should be good. All the others are used internally by at least one significant user, like for VPNs, or for example, T-Mobile uses 14/8 and 5/8, I think, internally. So it's the IPv4 that's left is not as good as the IPv4 that we had before. Anyway.
But they didn't allocate them, so.
Exactly.
So why should we pay?
Exactly, like /1. It's just the way it is. You get an IP address and it's bad because you will get traffic to it even if you don't ask for it. It's just
Yeah, but you
bad
always
idea.
get traffic you don't ask for.
So filter
Yes,
that,
of
so
course.
filter at their perimeter.
Of course. There are
Actually-
solutions to that.
Bounce it at their perimeter.
All right, you do that. Okay, so some of us are not convinced that this guy is calling, it seems. So anyway, you you have today you have two internets. There is the IPv4 internet and there is the IPv6 internet, and they're incompatible. That's what I wanted to say. So what you did if you played with IPv6 is you probably had native IPv4 and you got a tunnel to IPv6. And maybe you even used Freenet 6 as your tunnel broker. We're the guys behind Freenet 6. And then suddenly maybe you started liking IPv6. Maybe it's the absence of NATs. Maybe it's the idea of a brand new internet with nobody on it. It's like you're the first to arrive at a party. Maybe it's the addresses, the hexed addresses that nobody can remember except you, and you like that. And now you've become an IPv6 zealot. So you're liking IPv6 so much that you're thinking, if only I could shut down IPv4 forever, I wouldn't have to deal with all these NATs and everything. And I could do everything I want, all on IPv6. And this is what my project is about. Just a second. Okay. So Ecdysis, it's a project funded by NLNet Foundation and Virginie, ourselves. And it refers, the name Ecdysis refers to the molting of the cuticulae in arthropods as an analogy of IPv4 molting into IPv6. After molting, the arthropods is a kind of insects like spiders and all these stuff. Oh, spiders are not insects. Anyway. So after molting, the arthropod is fresh and ready to grow. And it's also the expertise of the 5-year-old son of one of the project leads. So, it's about DNSS64 and NAT64. What you want to do if you want to shut down your IPv4 access is that you want to only have an IPv6 network and access the IPv4 internet using a NAT from IPv6 to IPv4. And this is an old idea. Everyone, when you learn about IPv6, you think, oh, if only there was a translator between the two. And this was the idea of NATPT, NAT Protocol Translation, which was deprecated about 3 years ago. It was a bundle of DNS application level gateway and the NAT together, which talked to each other and shared state. It attempted to be a solution to everything. So any kind of situation, connection initiation from IPv4 side to the IPv6 side, and from the IPv6 side to the IPv4 side, and it did that by creating a mapping in the NAT when it received a DNS query. And it didn't scale. It didn't scale because it had to inspect all packets. It had to be, well, it had to be on the default route. It had to have access to everything, and it inspected everything going through it. So that's why it didn't scale. And so that's basically why it was deprecated. And now the ITF is working, well, it is finishing the work on 2 new protocols to replace that. It's been split in 2. There's the DNS64 part and the NAT64 part. And they're completely separate, so you can have a DNS64 box and a NAT64 box, and the 2 are not communicating with each other at all. And it only tries to address the case of connections initiated from an IPv6 network to an IPv4 network. So servers are on IPv4 and clients are on IPv6. And it only touches the packets that it needs to. It's not inspecting all packets as they go through. All the packets that it will receive need to be translated. So this is an example of how you will set this up. This is your perfect IPv6 network with your clients, and this is the yucky IPv4 internet with the servers on it. And you would put the NAT64 and the DNS64 boxes at the border. And connections initiation is always in this direction. And here's a simple example. I picked some addresses. Your IPv6 network is a /64. Your NAT64 it's not necessarily the default router. It has an IP on the IPv6 network. The DNS64 also has one, and you have a pool of public IPv4 addresses that are used by your NAT64. And you have a prefix, the pref64, it's usually called that way, and this is where you will embed your IPv4 addresses. So it's usually a /96, and all the 32 bits at the end are used to encode the IPv4 addresses, and you route that prefix to the NAT64. Here's an example flow. Everything starts by a DNS query. If you're not doing DNS, then this cannot help you. You would have to statically use the addresses in the pref64 prefix. So everything starts by a DNS query. The IPv6 client makes a query query to the DNS64. The DNS64 relays the query to the authoritative DNS server, which responds here, for example. This is not good. Shouldn't reply NX domain. Should reply empty answer. So, wrong example. Okay, so let's say it replies, for example, an X refused, and an X refused would not be interpreted like an X domain. So then the DNS64 tries by itself. It initiates an A query for the same domain, and there is an answer for that. And the DNS64 takes that IPv4 address and synthesizes a quadratic record with that. It's been appended here. This is taken and put here, and this is actually valid IPv6 notation. And the synthetic responses relate to the client. And then the client, for example, here initiates a TCP connection over IPv6 to this IP address. So it's routed to the NAT64, which allocates a NAT binding, translates the IPv6 packet to IPv4. The destination is extracted from the destination here, from the last 32 bits. And the source is the allocated NAT binding, and you see the ephemeral port here. And the exchange goes on, and just like a usual NAT. And it can also be used in the reverse situation, where you have the IPv6 internet with clients to your old IPv4 network with legacy servers. For example, you want to provide IPv6 access to it, Maybe you have an old printer. Printer are not going to get update firmware to give them IPv6 addresses. So this could be one way to do it. Another graph to really illustrate the two routes. So the NAT64 and the default router are not the same. This is important. So you route the default route to your IPv6 router and the prefix to NAT64. This prefix here, 64FF9B, is the well-known prefix that's going to be allocated by IANA. It's been chosen because, well, first, it starts with 64, so it's easy to remember, and two, it's checksum neutral. So in the NAT, if you use that prefix, then you can skip the checksum adjusting steps. And there is no shared state between the NAT64 and the DNS64. So Ecdysis, what we did 3 DNS64 implementations and 3 NAT64 implementations. For the DNS64, we have a standalone implementation in Perreault. It's really quick and dirty. It has many bugs. It's extremely slow, but it works and it's very fun to use as for experimentation. If you want to develop new features, you can try them on this. It's very, very easy. We also did the patch against ISC Bind and the patch against NLNet Unbound, which are 2 DNS servers used in the wild. And we did 3 NAT64 implementations. The first one is in user space, and it uses the TON device, and it's not open source right now. The other 2 are. We have a patch against Linux. It uses Netfilter hooks, and we have a patch against OpenBSD, and it's right into PF code. Some more words about DNS64. All connections need to start with a DNS query. If you don't do DNS, you have no translation. This is very important. Also a note about DNSSEC. Because DNS64 synthesizes records on the fly, it just breaks DNSSEC. Unless, if your client trusts the DNS64, then you have no problem. If your client wants to do its own validation, then it either has to, if it wants to do its own validation, it has to know about the DNS64 prefix that's currently used, so that it can realize, oh, this is really an IPv4 address, and I can follow the IPv4 chain of trust. Otherwise, the DNSSEC validation by the client fails. Just deal with it. It's a transition technology. It's not going to be used forever anyway. Okay, about our implementation in Bind, we had to make some pretty heavy changes in the core state machine of Bind, in the query find function. We added a new configuration variable, DNS64 prefix. So if you want to use DNS64, all you have to do is add one line in your options stanza. You just write DNS64 prefix, your prefix, and that's it. If you don't add this line, then DNS64 is not used. In Unbound is new. It's a new server, and it's very modular. Everything is in a separate module loaded at runtime. So what we have been able to do is write all our DNS64 code in a separate module, which by default is not loaded. If you're not using it, you're not paying for it. In Unbound, there are 2 other modules that come by default. There is the validator.so, which does DNSSEC processing. If you're not using DNSSEC, you just unload that module. And there's the iterator, which does the recursive DNS resolving. You will want to use this module at least. And what you do is, how Unbound works is it places all these modules in a single, in a chain, and all the requests that come in traverse the chain. And each module is a state machine. It can choose to pass the request to the next module, alter the requests, and so on. So you place DNS64 at the front, and what it does is it modifies quality responses. If the quality response that it gets from the modules further down the chain don't contain anything in the answer section, then it creates a new A record, A query, and when it receives that response, it synthesizes the quality records and finishes the processing. So this is probably cleaner than the one in Bind. A few words on NAT64. Did I say that before? Yes, I mentioned the well-known prefix. You can also use your own IPv6 address space instead of this. For example, if you have multiple NAT devices which don't share state, you will need to use multiple prefixes. So you just take part of your own IPv6 allocation and use that. And it can be shortened than /96. /96 is the bare minimum to encode an IPv4 address at the end. But if you want to do fancy stuff like routing on part of the IPv4 address, you could use, for example, a /56, which would leave you a few IPv4 bytes before the /64 mark. So you could route some, I don't know, you can do fancy stuff with that. Yeah, and NAT64 is precisely specified. NAT has never been specified at all. It's just, let's implement NAT and everyone does it in different ways. Whereas NAT64 is very precisely specified, and it tries to make NAT traversal easy. The big problem with NAT currently is that you cannot receive incoming connections. Everybody's fighting with that every day. With NAT64, it tries to be more gentle NAT. Our first implementation, it's very intelligently called NAT64D, and it's in user space, and it uses the TON device. It just creates a TON interface, and you route your prefix, your pref64, and the IPv4 address that you use to create the bindings on that interface. It's portable without too much effort. It works on Linux and OpenBSD now, but it could conceivably be ported even to Windows if we had the interest. It uses 3.h for its mapping table. It's very simple. You send it a USR1 signal, it prints its mapping table to standard out. If you give it a sig hop, it will flush its session table. Very simple. It's easy to develop new features. It's easy to experiment, and it's portable, so it's pretty cool. Our NAT64 implementation as Linux was quick and dirty. We just took our NAT64D code, we put it in a module in the kernel, and we replaced the TON IO with Netfilter hooks just to get the packets. And we do output on a dummy NAT64 interface, and you have to route. You then have to route the packets to their destination. On OpenBSD, it was first more interesting because it's the way we tried to do it the right way, and PF has many assumptions that we ran against. This is a quick graph of how PF works. It does its processing in two steps, in input and in output. The big problem that we have is that, okay, I will continue on explaining PF. For example, if you have an RDR rule, the first packet that will create state will be processed on input, and PF will change the destination on input, and it has to do that because the destination is used for routing. When the packets return on that same flow, they will be processed on output because it's the source that now needs to be changed. And it's completely the reverse for NAT rules. So we have, okay, and the keys that are created, the state keys that are created, they have, the lookup is, I call them straight and reversed. So you have normal or straight lookup on input and reversed on output. So you have a bunch of ifs everywhere. And if they all sum to 0, then you do straight. And if all these conditions give 1, then you're odd or even. It's always a bunch of, like a hypercube with many dimensions, and you just check if your number of dimensions is odd or even. And what we ended up with is adding another dimension to this hypercube. You'll maybe understand later. So we had to do 2 big hacks, because what we need to do is always translate on input, because we cannot do routing on the incoming packet. We always need to do routing on the translated packet. So what we need to do when, for example, when we create a new flow, so we have an IPv6 packet coming, we take this IPv6 packet, create the flow, translate it into an IPv4 packet, take the IPv4 packet and feed it back into IPv4 input, and have it go through PF one more time. And we drop, well, not strictly drop, but we ignore the original IPv6 packet by returning null. This is rather clean compared to the other hack. The other hack is that the key that we create has a straight wire key and a reversed stack key. This is so that the stack key matches returning packets on input rather than output. I see someone crying. Okay. So we always match on input, create the new packet, and feed it back into PF. So, and we notice that these half-reversed keys are recognized by their address families. If the 2 address families don't match, then it means that the keys are reversed. So it needed many checks everywhere to check if the address families are equal, and if not, then reverse the direction of the match that we previously thought we needed to do. So this is what I call adding 1 dimension to the hypercube. So eventually what we end up with is something not so clean, but it works. And we're currently investigating cleaner ways of doing that. But the configuration syntax is pretty clean. It's just like the usual NAT rule, except that you use NAT64 instead of NAT. And after release 4.7, it will become a match rule using the NAT64 keyword. And we also have an RDR64 action plan for future work. And we decided to add a new action keyword instead of just implicitly understanding that, oh, this is IPv6 and the other side is IPv4, so we need to do NAT64, or even implicitly tagging it with INET and INET6. We decided to add a new action keyword to ensure that first, the NAT action always does what we're used to. So NAT from IPv4 to IPv4. And also to not imply that NATing from IPv4 to IPv6 is possible, because it's not. It's not, I mean, in our code. Quick comparison between our implementations. Our user space implementation is very close to the IETF specification. It tries to do everything by the book. And our Linux implementation also, because it inherits the features of the user space implementation. The PF implementation is different. It behaves like PF used to. So the advantage is better scalability. You can have more bindings on a single IP address. The disadvantage is that it's harder to do NAT traversal. But this issue is orthogonal to NAT64. You have the same issue on NAT for IPv4. And the PF implementation is better integrated with the rest of the operating system. So it works with the user space tools like pfctl and system and so on. And you can have state synchronization using pfsync. You can have carp, all these stuff. One interesting thing that you can do with NAT64 that it's pretty cool. You could have multiple cart pairs of NAT64 boxes, assuming you have a ton of traffic that you want to NAT. You can have multiple cart pairs of NAT64 boxes, each pair having its own prefix, and the DNS64 would pick a prefix either at random or round robin or whatever, and direct a flow to one NAT64 pair. It's very easy, cheap, and it's planned for future work. A few lessons that we learned. Things that work behind IPv4 NATs, you cannot take for granted that they will also work behind the NAT64. For example, if you have an address literal in web hyperlinks, this is actually fairly common, especially in intranet pages. People sprinkle IPv4 addresses all over them. They will simply not work because you're not using DNS first. MSN doesn't work. MSN doesn't work because the first thing it does when you register is it redirects you to another server by giving you its IPv4 address. So it doesn't work. And you have all these tons of IPv4 only applications. For example, Skype. Skype doesn't work behind NAT64. Also, you need to synthesize on DNS error. For example, you do a query and some fancy DNS servers, I say fancy because it's kind, and they don't like IPv6 at all, and they reply all kinds of errors. They could say serve fail, they could say NX refuse, anyway, so you should say refused. Anyway, they return errors, strange errors to queries, while being completely normal to A queries. So what you need to do if you want it to work with the servers that we have running on the internet right now is attempt synthesis even on errors. And there are the remaining minor glitches when you're on IPv6 only. For example, Firefox thinks it is offline if you only have an IPv6 address. For example, on Mac, the connecting icon, I don't remember exactly where this is, but you know, there are some icons sometimes that spin and say, oh, I'm waiting for the HTTP address. It's waiting, but you're never going to get one because you already have an IPv6 address and you have access to the whole internet on it. So these are minor glitches that will get smoothed. So, okay, conclusion. So NAT64 is usable now for the style of browsing that we call web and email. The code is available on our website. You can try it and you can fix our bugs for us. And we love patches. Please send them to us. Our goal is to have it clean and ready, be able to be integrated upstream. If you have any questions, send me emails, see our website, and special thanks to NLNet Foundation, Brian McBride, and David Webb. Thank you. Any questions? Yes.
Do you remember what the problem was with our other solution? Maybe you can talk about that.
Okay. One idea that Ryan had for a cleaner solution was we could do basically like IPv4 mapped IPv6 addresses do, which is tell the kernel that you need to apply IPv4 routing. Well, okay, first, I noticed that IPv4 mapped IPv6 addresses don't do that, but this is how I think about it. So if we could tell the kernel that for a given IPv6 prefix, you apply IPv4 routing on that, then you could feed the kernel IPv6 packets. It would apply IPv4 routing, and then you would translate the rest of the packet. You would only change the address first, and it would all be fine. The problem with that is, how do you do the reverse? You have a packet coming from IPv4, and you want the kernel to apply IPv6 routing? No, you can't do that. So
You just follow the states, the PF states back to the same where it came from.
yes. So we're almost up to where I was, where I thought that, oh, there is a problem.
We'll always have problems.
We need to talk.
Yes. Yeah.
Any other questions? Manifestations of interest? Manifestations of disinterest?
Did you do performance testing?
Yes.
The userland code versus the PF code?
Yes, the PF code is 6 times as fast. And it's also 6 times as fast as the in-kernel Linux implementation.
It's hard
So-
to get a point of reference.
the user space implementation and the in-kernel Linux implementation are just about as fast. So it would mean that our code is not optimal, I think. It cannot only be explained by OPF is. I think it's our code. That's our fault. That's our fault. Yeah. We did also performance for DNS, and DNS64 is just a bit faster than normal DNS. I can't explain it. I can't explain it because it should be exactly as fast, because we cache the responses that we synthesize. So everything is cached. It's all coming from the cache. And our responses, they're quad-A. And I benchmarked that against A responses, which are smaller. And the synthetic quad-A responses are faster than A, and they're right. So I don't know what's happening there.
But I do have a question.
Yes?
How are you going to convince people to use this particular mechanism? Right? Because this requires work on
Yeah.
both ends.
Yeah. There has been a lot of interest from greenfield deployments. You have a new mobile phone, whatever you want to expand, you ask China for 10 million addresses and they laugh at you. So you think, if only I could give them only IPv6 addresses, but still give them access to Google. This is one use case where there is a lot of interest from that. The other interest is coming from ISPs who want to switch to IPv6, but they don't want to do dual stack either. We've been telling people to install IPv6 and do the dual stack thing for a long time, and it hasn't been done. And we're at a point where people realize that they want to switch, but they don't want to run two networks because it's costlier to run two networks than just one. So what they want to do is just go straight from IPv4 to only IPv6. And do this overnight and install a NAT64 for the Google access. Actually, I'm always saying Google, but if you're an ISP, you just tell Google, I have IPv6 addresses, and please give me IPv6 access to Google, and they will reply to your DNS queries, to your quad-A queries with IPv6 addresses. So any ISP who wants to turn on IPv6 and wants to get traffic on it can get all its Google traffic on IPv6 overnight. So this is, I don't know, 30% of your traffic going over IPv6 overnight. So, and there is the hobbyist who wants to never deal with IPv4 ever again. So we're not doing any convincing. I've been joking earlier about, telling you, hey, the sky is falling, but I'm not trying to convince you at all. People are asking us to implement this for them. Yes.
You're implicitly trusting DNS, and yet it falls apart when you use DNSSEC. So, have you thought about the security implications of that?
Basically, it breaks DNSSEC. That's it.
I now support this. I drop all my objections. It's complicated.
All this is based on the assumption that you don't want to change the client. You want the network to do it for them. If you can update the client, then they will just get their tunnel and you're done. You don't want to update the client, and so the client cannot know that there is this special prefix for which I should do DNSSEC. If you could update the client, then you could tell it about this special prefix. So this is a transition technology. It has many flaws. It's a NAT, but it's harder than NAT44. It's NAT64. So it has flaws, and it's only temporary. You don't want to run this your whole life.
So how long do you see this being used for?
I can't tell. We're at the beginning of this. I don't know of any real deployments of this. So I don't know how long it will last.
Microsoft is a company that spent a long time actually playing with dual stack technologies, and they didn't go very far with it. Eventually had to abandon all the Bell networks and all the other things that they did. And
You mean IPX and IP?
Yeah, and even before that, we had all the archive sort of stuff too. So dual stack has always really hurt people, and they've eventually abandoned them.
Mm-hmm.
And here we are, probably 15 years in, of trying to deploy a dual stack technology
Yep.
on the entire internet.
Yep.
And we're just running into more and more intractable problems.
Yep. People,
Fascinating.
we have underestimated the difficulty of running dual stack. Definitely. Anybody else? Thank you.